All right. So welcome everybody. Today I will characterize Josephson effect. So you already know what is superconductor. It's essentially the system that manifests macroscopic quantum effect. Is a superconductor. Similar type of system that has macroscopic quantum effect is superfluid system, and also the similar system is Bose-Einstein condensate of atoms. So all these three systems have one thing in common, and this thing in common is that so in a sense, big body behaves like a big size wave function, Schrödinger wave function. And this function can be linear or nonlinear, and let's say it will turn out to be nonlinear actually, but then there is a possibility that you take such two systems having macroscopic quantum Hall effect and you couple them in a weak way. And this coupling is expressed by currents, electric or mass current, and this will be named as Josephson effect. Okay, but let me first go to Josephson and the story associated with him. So here there is again the same slide about superconductivity. So you have Nobel Prize winners on the right side. But basically, this Josephson effect was discovered in 1962 at the University of Cambridge. Josephson was student of Anderson, also Nobel Prize winner, and also so this was jointly discovered with Javert, in a sense that Javert tried to disprove Josephson. So this you have Josephson and Javert. So in a sense they are fathers of Josephson effect in superconductors. And later there was Nobel Prize given to them in 1/3, and the third person was Esaki. So there was tunneling diode in semiconductors. So there was Nobel Prize for usage of tunneling effects so tunneling effect was used for new devices design. And Josephson effect is like Josephson junction is a kind of as important element as transistor in case of semiconductors. So Josephson junction is occurring in systems you can build in systems with having macroscopic quantum effects. All right, so this is a short overview, and then let me move on. Yeah, so then there is a definition of Josephson effect. So I would say two physical systems exhibiting macroscopic quantum effect coupled in perturbative way by some narrowing are constituting the Josephson effect. Well, then there is arguing how to start with this description, and then essentially we have left and right superconductor, and there is insulator in between. I would say that this insulator in between can be a kind of insulator like, for example, PB203. This could be such insulator. Or this could be less superconducting part. So let's say it could be superconductor that was irradiated by heavy ions that destroyed superconducting lattice. So this region in between is less superconducting. So it doesn't have to be insulator in a strict sense, but it has to be a system of less superconducting. So here it's tunneling Josephson junction. I hope that you see my arrows. And if there's anybody in the waiting room, please let me know, because I believe I admitted everybody. So this is there is so this is tunneling Josephson junction. So it's a sandwich between superconductor, insulator, superconductor. But so this is in such a system, this thickness of this insulator is supposed to be in the range of 50 nanometers, let's say. And so then the electrons can effectively tunnel from left to the right. Actually, Barden was against existence of Josephson effect, and he tried, by his experiments, he tried to disprove Josephson argument, but actually he has proven. And also, so Javer was experimentalist, and nevertheless, he was still given Nobel Prize for discovering something new. And also I would say, the Barden was against this idea. Barden was Nobel Prize winner for BCS theory of superconductivity that was described last week. And so sometimes, and Barden was already double prize winner, so double Nobel Prize winner can be sometimes even wrong. So anyway, so this is tunneling Josephson junction, the left side. The right side is so-called weak link. So there's some narrowing of between two superconductors. And basically this narrowing diameter is supposed to be in the size of less than one superconducting coherence length. In such a way, this region, let's say that this region is less superconducting, so it's effectively non-superconducting or something like that. So basically, also you can also place in the sandwich superconductor, insulator, superconductor. You can replace this insulator by semiconductor, and this still will be a Josephson effect. Or you can place metal, non-superconducting metal, and still will be Josephson effect. It's so I would say very general definition is superconducting area, less superconducting area versus superconducting area. Well, and also this could be expressed in terms of superfluids. But I'm not going to, and also Bose-Einstein condensate, which I'm going to just to mention, but I'm not going to describe those physical systems in great detail. So yes, and then there is a superconducting order parameter on the left side. That's a complex value scalar wave function. It's PCL, which can be characterized as the square root of density of Cooper pairs of rho L. So this is square root of density of Cooper pairs on the left side times e to the power of phase on the left side. So this is like wave function on the left side. And on the right side, you have a similar situation, but there is a density of Cooper pairs on the right side. So, and then there is a phase. And then the phase plays very important role. And you will see later how this phase is connected to vector potential. So actually, what is the way you are going to control this Josephson junction will be by controlling the phase difference between left and right. And then, oh, professor is coming. So you have these two superconductors coupled, and then there is a circuit which can approximate those phenomena. Especially, I would say, the circuit shown here will. So this is resistance in parallel to capacitance in parallel to ideal Josephson junction. This X crossing. So the system which is here is parameterizing the structure on the left. So imagine for a moment that the whole structure stops superconducting. When it stopped superconducting, then there are metal insulator metal. So of course it's a kind of capacitance at some point, but also it's some resistance, because if this insulator layer is thin enough, the electrons will move across it, of course generating some resistance. So then even above critical temperature, those elements R and C are in parallel, right? And then this Josephson crossing will disappear. So this is to give you intuition how to parameterize such a structure. Contrary, on the right side, you're supposed to replace this conductance, this capacitance C, with inductance, since you have a whole material that is uniform. So essentially, you have to replace C with L, with inductance. So that are some just general comments that I'm giving to you. So this structure the circuit structure will be later named as RCSJ model, resistor shunted capacitance Josephson junction, and this structure will describe properties of Josephson junction. Properties of Josephson junction in reference to two-fluid model. So two-fluid model have one assumption, that we have a assemble of electrons that are paired, so they create a Cooper pairs. So Cooper pair is a kind of quasi-boson, or let's say it's a boson. So Cooper pairs are subjected to Bose-Einstein statistics and so on. And this is like Bose-Einstein first state of occurrence, this superconductivity, condensate first occurrence. And then there is another fluid, which is a fluid of unpaired electrons that can move freely across metal or material, and they're unpaired. So they are fermions. So they generate small dissipation. So that's why it's two-fluid model. And if you have equation number 3, we are going to derive this equation. So this lecture is divided into 2 parts. One is just slides kind of way, and second is a little bit some of the computation. So yeah. All right, I see that that my face is not visible, but my camera. All right. Yeah. So can you see my face now, or not so much? Hello, Eric.
Yeah, we can see your
all right.
face.
Okay. Okay. So and still okay. So then there is this Hamiltonian, which describes the structures given over here. So this is equation number 1. This Hamiltonian will have left-right, Hamiltonian of left system, like left superconductor, Hamiltonian of right system, and the tunneling term. And then the state under consideration is like so this is like wave function of or the parameter is a superposition of wave function of left and right. So this is equation number 1. Equation number 2 expresses you this Hamiltonian term. So this is in a spectral form. So you have L stands, so this is L, EL, and this is bracket L. So this is like eigenenergy of left system. Then there is plus ER eigen and R ket bra. So this is eigenenergy of right system, and then there is a tunneling term. So satisfying tunneling term is simply throwing state from left to right and right to left. So this is essentially the tunneling term is exchange of Cooper pairs between 2 systems. I just maybe should stress one more thing, that you can have 2 superconducting grains in not so big distance. So you can replace insulator with vacuum. And if this distance is not too far away, there will be tunneling of Cooper pairs still present. So then what's you're supposed to know. And then there is equation number 3, which works actually with Hamiltonian too, but this will be explained a little bit later. So this is the total current flowing via Josephson junction is the term which is flowing via this X crossing. This is sign of phase difference between the right and left. This will be quite a new feature to you. Then there is a dissipative current. So this first current is purely, you can see, well, bosonic current, Cooper pair. This is Cooper pair current, this sign. And then you have some level of resistance. So Cooper pairs doesn't generate resistance. Cooper pairs moves without friction. So this is like superconducting superfluid that moves without friction, you can say. And then there is a dissipative current. So you will see later why. So this is voltage over R, but in relation to phase difference. So this is current flowing via this resistor. And then quite obviously you have this current voltage characteristics for a capacitance. So this is the first thing. So you have those 3 terms which constitute for RCSJ model. RCSJ model is very powerful in terms of efficiency because it's simply, this is nothing else as nonlinear pendulum equation. And you can like in Professor Hannes Telfer group or in Professor Yoshikawa group from Nagoya, from Yokohama University, you can have thousands of Josephson junctions on one chip, and you can express their interaction quite effectively by this equation number 3. But then, of course, you have systems of coupled equations. Well, so this is a phenomenological but still effective model. And now you need to so now the purpose of my talk is to give justification for this equation and how to derive DC and AC Josephson relations. All right. Okay, before coming further, I would say some people used to say that physics is mathematics. I disagree. Let's say this is because mathematics has to describe reality, not reality has to describe mathematics. So idealistic way of thinking, like Plato way of thinking, is that the whole world needs to follow the rights of mathematics. So like in Pythagoras, let's say, religious movement, they believed in ideal ratios so the whole world was described by sphere. So then the whole reality has to fit mathematics. But actually, in Aristotle's way of thinking, I would say you have physical phenomena, and then you find the mathematical tools able to describe it. So this is the slide which gives you different type of theories describing superconducting. So at the very bottom is two-fluid model, this RCSJ model essentially, which presumes existence of normal superconducting phase. On the top of it is Ginzburg-Landau model, which is going to be described next week or the week after next week. It depends on our speed today. On top of it, we have Bogomolov-Dijon equations, which are basically coming from BCS theory. I touched BCS theory last week. Perhaps some of this I will still redo later in greater detail. Then from BCS theory, you have a couple of theories like Gorkov propagator. So this is green function theory. Eilenberger propagator, so simplified Gorkov propagator, and then Usadel propagator. So Usadel is for kind of dirty superconductors. And then, and actually on the top of BCS theory, there is Eliashberg theory, which is more detailed theory of pairing. So you remember the pairing mechanism from last week. It was very highly simplified, and this is less simplified but Eliashberg theory, where you have whole spectra of vibrations of crystal lattice. And then on the top of BCS theory, there is Hubbard models. So basically, they can derive BCS and other. So Hubbard model is also essential. And in the meantime, you can also see things in an equilibrium way by path integrals on real time, on imaginary time, and on complex value time. That accounts for temperature difference and temperature time dependence. I'm not going to touch it. I'm saying that I'm going just to hit the bottom of these theories. But every Josephson effect, in principle, could be described by all this hierarchy of theories. And what will be the difference when you move from bottom to higher level of theory is that bottom has simple mathematical structure. And so this mathematical difficulty is increasing, and this is increasing, and also, but the level of a description of reality is also increasing. So for some people, it's enough to describe moving vortices in Josephson junction, for example, by time-dependent Ginsburg-Randall equation. But some people will say this is not enough. You need full dynamics of quasi-particles, which is by Bogoliubov-Dijen equations, and so on. So you will see later. It takes time to accommodate those mathematical models and to master them properly. All right, let me move on. So I'm going to hit the simplest possible models at the very beginning. Okay, and this is picture from one of my papers on Physicas of Solidity B 2012. And then I was working on a system where I have superconducting strip, and on the top of that there is ferromagnetic strip. So what does happen is there is diffusion of let's say magnetized electrons, let's say with some certain spin orientation, normal electrons from ferromagnet into superconductor, and then there is a diffusion also of magnetic field. So what is the result under this strip is that there's induction of quasi-normal phase, so superconductivity is destroyed. So this strip is actually making this constriction, this narrowing, which was explained at the very beginning. And then there are two regimes of the system description. It's like weak link regime, when you have two needles connected. So this is like weak link Josephson junctions. Or when this magnetic field penetrates very deeply, you have superconductor, non-superconductor, superconductor. So this system, independence on external magnetic fields you place it in, and independence on the thickness and temperature of the strip, thickness of those strips and temperature, you can describe the different regimes. Also non-trivial thing is that you can have ferromagnet like iron, but you can have also insulative ferromagnet. So there will be also different mechanisms. I'm not going to go into details because like this picture is described by extended Ginsburg-Randall model, which can be derived from Hubbard model, but this is how it is. All right, so just to broaden your imagination on the Josephson effects. Okay, then so I'm now first pointing out a couple of phenomenological things, phenomenological effects, which occurs at the same time as long as we talk about Josephson effect, and then I will try to move towards compact mathematical way of describing it. So you have left superconductor, in the middle right superconductor. So what you have is there is a phenomenon of so-called Andrew reflection. It will be a very magic one. So you have this system of normal versus superconductor. So basically, you have superconductor normal, superconductor state if we have Josephson junction. But let's say at the very beginning that you have this case of normal metal versus superconductor. If you have incoming electron that has energy below the energy of Cooper pair gap, which I have described, superconductor gap, let's say, then it is going to be reflected as Hall. So this is very amazing phenomenon. So what happens is electron that has spin up is reflected as a Hall that has spin down. But why is, and then there is induction of movement of two electrons that are in pair. This is a Cooper pair. And so what is essential here is that during this reflection process that is non-dissipative, you have coexistence of there is preservation of energy momentum and angular momentum. So since in superconductor essentially Cooper pairs only can move, then in order to have charge preservation, you need to have this such configuration as here. And then also the Cooper pair has angular momentum 0 essentially. And this is the same of electron and Hall, because the Hall is like anti-electron. So this is very essential phenomenon. And there is also argument very much aligned with CPT symmetries, preservation of CPT symmetry, that you can change charge conjugation, parity change, and time change at the same time. So one of the Feynman interpretations on existence of antiparticles is that antiparticle is a particle of opposite momentum moving backward in time. So this is in a sense Hall in very essential ways is antiparticle to electron. So when Hall and electron are met, the recombination takes place. So emission of some radiation or some additional phonon vibrations takes place. And also you should know that electron is lack of Hall. So yeah. Right. So this is Andrew state, Andrew reflection, and then this process of relaxation is, so this is going back and forth. So this electron is moving from left to right. It's reflected as a Hall. It moves from right to left, and this Hall is reflected and it's moving. So this is moving back and forth. So you have wave packets as described underneath. And then there is certain thickness of this junction, and then you have moving of the whole Cooper pairs on the left and right, as you can see here. And this is actually this exact picture of Andrew bound states is provided by Bogoliubov-Dijon theory. It's not provided by RCSJ theory, is provided by Bogoliubov-Dijon theory. So RCSJ model is missing this part. This is very important for you to know. And second thing, which is always problematic from quantum mechanical perspective, is that the theory of resistance, of electrical resistance, described very fundamentally basing on quantum mechanics is very troublesome. So the description of dissipative processes by quantum mechanics are troublesome. And there's various reasons, size of Cooper pair and so on. I'm telling you that this still now it's a challenge to do it, especially in big scale. Anyway, you know so Andrew bound state described on the slide constitutes the Josephson effect existence. So this is a very important message to you. All right, and then now we will try to become more exact by detailed derivations and computations, right? Then in this meantime, there is famous metrological triangle given here. This is very important in the context of quantum metrology. Its connection between Josephson effect, single electron transistor effect, or the electron flow effect, and there is quantum Hall effect. And okay, so my kind of, let's say, expertise is mostly on the side of Josephson effect, and also quite recently also I get expertise in single electron devices, and I still do not have full expertise in quantum Hall effect. Nevertheless, those three phenomena are interconnected. And then I should supposed to mention to you that if you apply voltage to Josephson junction, what happens is that if this voltage is it's less than this, of magnitude smaller than the size of superconducting order gap, there will be induced oscillations. So you will have voltage controlled current oscillator, Josephson junction. And then you can generate high frequencies of oscillations up to a couple of gigahertz, sometimes even you can go to terahertz regime. And this is in regard to high temperature superconductors. So this is superconductors, Josephson junctions, especially in D-wave superconductors, can be the source of terahertz radiation. Nevertheless, there is a problem with high power of this radiation. Then there is single electron devices. This is semiconductor single electron devices. There's charges, flow is quantized, and also there's quantization of resistance, as you can later see. And then there is a quantum Hall effect, where you have this, also very specific connection between voltage and current, and there we have specific steps in conductance in quantum Hall effect. One of the best specialists in quantum Hall effect is Professor Dietl from Polish Academy of Science in Warsaw, and Dr. Zgierski was collaborating with him for a long time. Yeah, so that's a phenomena of three. So here are frequency of oscillations, voltage and current. There's interconnected, and then all right. And then just to give you small insight is that you can have two Bose-Einstein condensates. Usually it takes nanokelvins to get a Bose-Einstein condensate. So you have some gas trapped in this, and this gas is achieving macroscopic wave function. And when you introduce some barrier between two of them, then you can have effect of tunneling. And this system here also shows, let's say, Josephson effect. But in terms of practicality, I would say the most practical are Josephson junctions made from superconductors, and they're able to detect single quantized magnetic flux, very small size. And then next level of practicality is superfluid Josephson junctions. And then the very last level of practicality are this Bose-Einstein condensate Josephson junction. So we have the layers of Josephson junction effect, and also you can find pretty other also systems presumably showing Josephson effect, but I'm not going to touch it. I'm just going to give you brief insight into this philosophy. Okay, then just let us refer one more time to this ferromagnetic strip on the top of superconducting strip. So here is the slides this is essentially IV characteristics, the middle and the right one by Dr. Luis Gomez. So you see this is clearly nonlinear current voltage characteristic. So this is specialized for, so this is for weak link, this middle one. However, you can have a peak and two other curves like here. This is for tunneling Josephson junction. And what is also remarkable is that when you place Josephson junction in external microwave field, you will have characteristic steps in IV characteristics called Shapiro steps. And this was observed for this ferromagnetic strip on the top of superconductor by Luis Gomez. And it is commonly believed in experimental community that existence of nonlinear current voltage characteristics and existence of Shapiro steps is sufficient criteria for confirmation of existence Josephson effect in the system under study. That's how it is. It's just, and we supposed to get also Shapiro steps from this from RCSG model as well, and using DC and AC Josephson relations. All right, and then how to tackle it. So I give you first the kind of conclusive remarks, and later we will do things step by step by derivations. So if you can have equations of motion, because you have two systems, so 2.16 is the same as actually it is from equation 2. Okay, and so you have a system of coupled equations expressing electron tunneling from left to right superconductor, equations 2.16. Then you have preassumption 2.17 of this existence of presumption giving the complex value order parameter and phase for left and right superconductor, and then there is evaluation how the number of Cooper pairs on the left side is changing, and it turns out that this is proportional to square root of density of Cooper pairs on left and right, and then there is a sign difference. And so relation 2.18 constitutes so-called DC Josephson junction, DC Josephson effect, and then so it simply says that relation 2.16 simply says that you need to induce phase difference between a left and right superconductor in order to maintain the current flow. So usually in semiconductors, in order to induce current flow, you have to apply voltage. So gradient of potential or voltage, basically voltage difference. So electric field presence, voltage difference. And here, and this is encoded in so-called Ohm law, right? That current density is proportional to voltage difference or otherwise to electric field presence. But if you have London relations, as it was already discussed, London relations point out that you need to have vector potential present across Josephson junction. And this vector potential is imprinting phase difference due to a Haranov-Bohm effect. And this phase difference is generating flow of current. So it's very surprising the driving parameter for current to flow via Josephson junction is presence of magnetic field. So saying in different way, you need external solenoid as a driving factor, so external solenoid generating magnetic field will imprint phase difference by presence of non-zero vector potential. Well, and this is how it is. And also there is a presence of AC Josephson effect. So that's answering to this question with phase difference depending on time, which accounts for existence of electric field, delicate electric field. I just want to underline delicate electric field, which will generate oscillations. So this is voltage controlled current oscillator naturally. So that's how it is. All right, so we are having such postulates as specified over here, and I suggest now to. So do we have any more questions in relation to the slides? Eric, do you have any questions?
No.
All right. If not, then let me continue by usage of this notes on. So now I switch to manual mode of let's say, yeah. So I need to change my cameras, yeah, and then that's strange. Does it react or does it not? Do you see my camera?
Right now, we see only the bureau at 10 watts per hour. So no.
Yeah. As that's kind of strange, but let me redo things because it will be much more problematic when it's not work. Okay, this is one, and then yeah, can you see now? Wojciech?
Yeah, right now is everything okay.
All right, sounds good. I hope this will be good enough to see. We'll see. By the way, there's this English surname good enough. This also I met such famous physicists surname. Anyway, all right. So let me start. So this is derivation of DC Josephson effect. All right. So what type of situation do we have? We have the Hamiltonian of the system, which is written as in this way, and so this is energies of two uncoupled separated physical systems, right? And then there is this tunneling term, which describes you this interaction between the systems. This interaction between two physical systems. So what I'm doing right now, it's perturbative interaction between two physical systems L and R, left and right. Of course, by default, we think about such a situation when you have, let's say, left and right quantum system, and then we connect, or yeah, this is what we think. So this is Hamiltonian. And this Hamiltonian can be written in matrix base, So we need to simply compute all these terms. So this is EL, then it's R, ER. So this is eigenenergy or eigenenergies left and right. And then we have this R L, the anti-diagonal terms. So those will stand for diagonal terms of, sorry, this will stand for diagonal terms of the matrix, and this will stand for anti-diagonal terms of so we have EL, it's over here. ER, ET, and ET. So we have such matrix, right? Wojciech, is it understandable, this form of matrix?
Yeah, right now everything is understandable.
Hopefully it is. All right, then and then that's, but then there is yeah, so the quantum state of the system is going to be Psi L plus Psi R. So saying in different way, you can write it that this is Psi times Psi, right? So this is effectively, oh, sorry, this is again, Psi is equal, so this is wave function. So this is superconducting order parameter, superconducting order parameter on the left side. And this is SCOP, superconducting order parameter on the right side. Yeah. So what we end up? We end up in such kind of spinor-like when those two quantities are complex value, of course. Complex value wave functions, you can say Psi and Psi. So this is complex value wave functions Psi, Psi, right? So we have things like that. By the way, a kind of similar way of thinking you can find in for sure you can find this in these things in Tinkan, and you can find in Barone book on Theory of Josephson effect. I really recommend you this book. But Barone book would imply that we need to have 5 hours of lecture time every Saturday, not 1.5 hour. And right, so that's how it is. And also, yeah, so now we are going to derive the equations of motion. Yeah, so I will write them, and then I will continue on next page. So basically, from a quantum mechanics, we have situation as here. It's very simple, right? Equation. But I think writing it simple, it's harder to make interpretations of certain solutions obtained. So what we have here is we have here d over dt with respect to this guy, L and CR, and there is a matrix EL, ER, AT, AT, and this is CL, CR. So we need to solve this systems of two-coupled differential equations, this guy. We need to solve it. And then we'll come into justification of AC and DC Josephson effect. Okay, so let me move on with that. Sure, I mean, I will rewrite it, those equations. So I am going to rewrite it in the following way. Is d over dt CL CR, and then you have so we have such structure of equations. Yeah, and by the way, here is one. We pre-impose solution. Because this is due to perturbative nature of interaction between left and right superconductor. So this is very important that we have pre-imposed it, because basically two interacting systems supposed to be entangled, and this is not exactly. Here we just sum, and this is like, imagine you have this. Yeah, I will make a comment on that in greater detail. Why it's like that? Because if you have superconductor left and normal, so what happens is that there is diffusion of Cooper pairs. Diffusion of Cooper pairs from left to center. So you have concentration of Cooper pairs. So this is this rho, L versus X. There is diffusion process. This is diffusion process. And similar diffusion is for the system of normal material superconductor, right? So there is also this. And then what you have here is superconductor left, superconductor right. So you have like distributions, and there's a superpositions of Cooper pairs from like two-wave functions. And of course, this thickness of tunneling barrier matters, because actually the level of critical current flowing via the junction depends on this thickness, and it's exponentially decreased with the size of this thickness. So if you make too big thickness, there could be zero current flowing, or so the level of critical current is the current after which I over exceed then I would, which I exceed, then I directly go into normal state. This is critical current of Josephson junction. All right, so now we have to simply do mathematics. So we have such system of coupled differential equations, and basically we have, and also, okay, and then we're supposed to know that this is rho L times E phase L, and ER is rho E phase right. And then, okay, so now it's my time to write those equations. And then rho L, so I'm just plugging in, right? No big deal. And simply saying EL, ER. And basically the strength of tunneling is encoded in these anti-diagonal terms. So the strength of tunneling depends on the distance, on the size of this non-superconducting material that is in between two superconductors, or the size of less superconducting material, and also on the size, so on how big is the structure, because we can make Josephson junctions of different sizes. So this is how it is. Yeah, so we have to plug in, and then so essentially one more time, if you just write down these equations, I will do this in this picture, EL CL plus this is perturbation, I would say. So this is perturbation, this term, and again d over dt. So d over dt, right, it is more exactly like that. ELF plus ER CR. So this is again perturbation. Okay, so I will simply move on 1 second. Yeah. Okay, let me move on. So we have the following system, and now we place, have to do with it. So we place, so we are solving. So this is d over dt rho L E EL is equal EL rho L EL plus AT and in analogical way, yeah, it's sufficient to do it in that way. ER I will make so far real value at this stage. So you will see later we can play with the solutions. Actually, it is all worth it to play with solutions. Physics is a little bit about playing with solutions. So this will be a system of two coupled pendulums, actually, as later. And then yeah, we need to, yeah, but this turns out to be nonlinear system of coupled pendulums. Okay, so we have such equations. So we need to make this derivative. The left side will be problematic, but we'll see. I will use this dot concept. First, yeah, e to the, yeah. And then If I'm wrong, please correct me. And then we have it. Okay, so of course this is minus h, but anyway. So this is the first equation. And the second equation will be pretty much the same because it has the same mathematical structure. Nevertheless, I need to write it down. ER minus and sorry, this is supposed to be there's L. Guys, by the way, you need to know this derivation. Otherwise, you cannot proclaim to understand the Josephson effect. There's no other way. You have to do it by your own if you really want to understand. All right, so again, so we have such systems of coupled equations, and well, we want to simplify it. Well, I would say we have to get rid of certain phase. So in case of first equation, I will multiply e to the minus both sides. And in the case, so I will try to drop this term over here. So to get rid of this term. And again here. So this I will multiply by minus ER. Okay, so let me proceed. So doing so, I get minus H. Yeah, I forget something, guys, and nobody is really protesting. Wojciech, is everything correct here? Derivative of such function.
Yeah, wait a second.
Is there a minus or not? Please confirm it. Can you confirm it or not? Guys, we need to be interactive.
Yeah, there is a minus. Yeah.
Okay. All right. Good. Good. So this is how it is, and then EL. Okay, this is so this is our first equation. I think it's quite understandable what has been done here. And the second equation goes almost immediately with that because, yeah, you will see. Because the structure, mathematical structure of the same equations so this is a system of two coupled ordinary differential equations, right? So actually, in case of rapid single quantum flux electronics, as developed by Professor Hannes Töpfer and Yoshikawa or Fujimaki in Japan, then it's sufficient to use this two-fluid model. Nevertheless, we can always go above this model because this RCSG model will generate you various families of current voltage characteristics. And to some of you, I have sent email yesterday. I attached some nice papers, including Josephson paper, Nobel Prize paper, but also I included some paper by Naga, by one of on this IV characteristics from RCSG model. Then you're supposed to somehow have some insight into it. All right, so what we have here is so we have basically such system of equations. Is it understandable? Hello, guys.
Yeah, it's understandable.
Right, and at first I will take imaginary part of both sides, right? Imaginary part, right? So this guy is imaginary and this guy is imaginary, right? This guy is imaginary and this guy is imaginary. Do you understand what I'm saying? Hello?
Oh, right now we can see what you marked.
Oh, that's strange.
Because you have to move a paper.
All right.
Oh,
so
yeah.
Okay, so we have a systems of two coupled equations, and we have imaginary and real part on the left and right side. So I'm going to take imaginary parts on both sides. You understand? I'm just taking imaginary parts, right? Guys, do you understand?
Yes.
All right. So doing so, I have minus EH over L is equal to sine AT sine times I, right? Wojciech, do you agree? Do you agree?
You can. Oh, yeah, I can agree.
Right? And then from another side, you have do you agree, Wojciech?
Please move a paper a little higher.
They are almost the same, right?
Yeah, I can agree.
Well, actually, so we can drop out this I, right? Right? And so we'll observe that. So this guy will be that minus this guy. Okay, will be 80 square root of L times R sinus. So this goes from first equation, right? This comes from first equation, right? Wojciech?
Yes.
All right. And then from the second equation, I can use this minus to make a difference between this. So second equation will be written like that. AT. And then I change the order of those two guys, right? Is sine x, you know that sine x minus sine x is equal sinus minus x, right? You know that, right? This guy,
Yes.
right? So that's why I use the sign to change the order of these two guys. And of course, so this simply means, So this is, do you see this this relation right now? This,
Yeah.
yeah, so that this is charge conservation, right? Eric, is it understandable that this is Eric conservation, that this is charge conservation?
Yes. Yes.
Right, which is good because this is actually a current and this is also a current, right? So you see the current flow is a change of density is proportional to, this is sine of phase difference between R and L. Do you see that? So this is very, so this is actually this relation which I derived. This is DC Josephson effect relation. So if you have zero phase difference between left and right superconductor, you there is no chance there could be current flow. This is very important paradigm because it's not obvious paradigm. Most electrical engineers doesn't know superconductivity. Forget it. And this is partly due to the fact that the knowledge of Josephson effect requires knowledge of macroscopic quantum effect as superconductivity, and then this refers to nonlinear Schrodinger equation like Ginzburg-Landau, and this refers to Schrodinger equation, and this refers to quantum mechanics, and some electrical engineers doesn't like quantum mechanics, so usually they skip it. So there's a certain level of ignorance, not all the time, because I will also mention you about EEE conference, quantum week conference in USA. But anyway, so this is very, very important step. And you guys, you need to know this derivation. You have to do it on your own. There's no other way you can understand. But that's also important that the current super. So this is what stands by this cross, which I have shown. This is current flowing via this cross. So this is superconducting current. I write superconducting current. So this is first type of fluid. And now we have to explain AC, another type of current. So hopefully it's understandable. So I will convey this message to next sheet of paper. 1 second. So this will be, I'm just, okay, this is not visible. I'm just, guys, rewriting this for you. And such a way of thinking is also done in Kittel, but it's better done in Barona than in Kittel, actually. Probably the best considerations are done Barona. And right now we omit green functions, but perhaps one day we're supposed to go into green functions description. Okay. And then just, I took imaginary part. Now I need to take a real part, and then we will see how things are. All right, so if I take real part, the things will be slightly different, right? You will see. Okay, so let us see. So I'm taking real part of both sides of equation. So what I have is, I have this guy, and so this I will omit, and then I have this guy. So this is equal, Yeah, this is, you agree? This is real part of both sides, right? It's real
Yeah.
part. And quite similar structure, almost the same will be with different equation. And the order doesn't matter anymore because this is cosine, right? Yeah. Yeah, and so what can I obtain? I'm very much interested in phase difference, right? So this order doesn't matter. So it's the same as, so this is the same as cosine. Remember that cosine x is equal cosine minus x, right? But I'm counting for phase difference dynamics of phase difference. How would it change? And now there is dynamics of phase difference in the situation when there is no voltage. I will later tell you how to do it with voltage. But what does it mean? That I can subtract these equations, or I can try to subtract that. Before that, I see that minus HL is equal ET RL cosine R minus EL, right? This is what I see. And the second equation is almost the same, but actually it's not the same. Did I miss something? No, I didn't. So this is T. Where's the transfer? AT. And here is cosine, and I can change this order because it doesn't matter. So if I subtract two, I will subtract it, and I will tell you that so H R, so I multiply by -1 and add it. So this is like that. So this is AT. So this is do you see this? What I have written here?
Yes.
So the phase difference dynamics is like that. So I can write HD over dt delta theta is equal to AT R L minus LR cosine delta T, right? So you see. But if we have symmetric superconductors, or density of Cooper pairs on the left and right side is equal, right? You have, yes, Wojciech, do you agree?
Yes.
So in that case, this simply means that this dynamics of phase change is 0. So phase is preserved. So this means that that phase difference is constant, it's not changing, right? Right?
Yeah.
for symmetric superconductors, right? Wojciech?
Yes.
But if they're asymmetric, there's always phase change. It's very important that when you place niobium on the left, which is superconducting, and on the right Pb, there will be oscillations all the time. So, yeah, of phase. But if you make the same material on both sides in similar time, is the same technological process. Is supposed to be the same. No phase change with time. So then there is a question: under which circumstances there exists phase change? Okay, and then I will answer. I will give you some hint. So if you apply, so you have left superconductor, insulator, right superconductor, SC1, SC2, insulator, and you apply minus V over 2 here, plus V over 2 here. So it's then so there is a voltage difference. Okay, so then I have to modify my equations. And so what does happen is this. Okay, I will write you this. In these equations of motion, the left side energy will be lowered and the right side will be increased. So this you will have V over 2 times 2E, and then the right side you will have, okay, so this will be AT, you will have increased times 2E. 2E is because there is a Cooper pair. So we have such equations of motion. So it will modify your okay, this self-energy term. Okay, so doing so, I will obtain the system of the following coupled differential equations. As before, I will just rewrite it. It's because everything will be pretty much the same, except the fact of I'm just rewriting our previous considerations. So EL minus V, E, let's say, this will be like that, plus AT ER E R minus L, and quite much the same, quite much the same will be here on the, so since the structure of equation is the same. All right, and then let me do it. No, I missed something. Sorry, there was no I here. No imaginary part here. So this is like this. ER plus VE rho, and plus this guy, and this is minus R. And now what? We need to use this voltage, knowledge about voltage. So we need to take real parts of both sides. And doing so, we have, okay, I would jump to a conclusion quite, well, this is R. Well, let's say, let us pre-assume that we have such densities. Doing so, we have okay. plus AT cosine ER minus EL. And this is the first equation and second equation. Dobrze. So we have two equations, and then we need to subtract them. We will do it. So then this terms doesn't matter because, okay, as I mentioned, this is raw. So when we subtract them, we obtain okay, I will write you in most, okay, this is like that. For symmetric superconductors, so we have it, essentially what we have it is, also symmetric superconductors means EL is ER. Symmetric superconductors. So what does it mean is that actually VE twice rho, this will mean this one, and this is, yeah, and then because of this term drops out, what happens is that H d over dt phase is equal voltage times 2E. So it turns out is that this phase difference is nothing else. Okay, so this is H over, sorry, this is H over 2E is voltage. So voltage is phase difference derivative times H over 2E. And this is AC Josephson effect relation. So we have derived those two equations that have been on the slides. We have derived them. Well, then, so making the summary of today's, we have established, so having this assumption of that such a system, so I'll make a summary. This is EL, rho L. Okay, so you have such system, and then there were equations. So you have defined such. So this is a case of two coupled systems, and there was Hamiltonian describing equations of motion in the following way: EL minus V over 2, ER plus V over 2 times 2E times 2E. And there is a transfer. And based on that, we had derived current flowing, SC, is AT. For a very small phase difference, sign of phase difference is the same as argument. So DC Josephson effect, it was established. And secondly, there was established this d over dt voltage time times 2e. So it was established that voltage. So this R minus EL is this guy. So this is AC Josephson effect. So AC Josephson effect was in case of symmetric superconductors. Symmetric superconductors. Yeah. So this is a message to be taken home. And those two models, and this is very important relation because it gives us, then we can evaluate what's the value of resistant current. I'm just going to derive right now this. I'm almost done. This is V over R. This is dissipative current, right? So you know from this relation that dissipative current is it's like this sign of this phase difference. So this is H over 2ER times, so this is dissipative current by going by R. And then with respect to IV for current voltage characteristic Q over V is equals C for a capacitor, you know that current is C times V dot for a capacitor. So this is C, and this has to be taken H over 2E star. So this is, and then DC Josephson current was already derived. So this is okay, I0 times sinus delta A. So in total, we have total current flowing through is this C plus C plus dissipative R. So this is actually sine delta plus to ER delta plus CH over 2E. So this is RCSJ model. So this is RCSJ model. RCSJ model derived for this junction. So this is actually, you can pre-impose externally what is the current flowing Josephson junction. So this is nonlinear pendulum. And this nonlinear pendulum becomes linear if this delta is small. So we have arrived to RCSJ model for Josephson junctions. All right. So do we have any questions in regards to, or any comments in regards to conducted presentation? Please go ahead. Radosław, questions? Are you with us, Radosław? Eric, some questions?
So will you share these notes with us?
You want
will
to
you
have
send these notes?
Yeah, I can make a scan of these notes, probably around Monday, something like that.
Mm-hmm.
Yeah. Is it understandable, the reasoning?
It's
I
okay.
think so.
Okay, sounds good. All right. So guys, let me meet in 3 minutes time after this, because I have just very short announcement to some of students associated with me. about some type of conference. So anyway, thank you for your attention. See you next week, and let us talk in 3 minutes. I will send you the link. Thank you, guys. Bye bye.